Look at your hand. Curl your fingers. Feel the weight of your own body in the chair. Now, consider this. Every single atom that makes you, every element of your blood and bone and breath, was forged in the heart of a dying star. We are not just living on a planet. We are stardust, temporarily assembled, gazing up at our origins, and for a brief, brilliant flash in our history, we decided to do more than just look. We decided to go. This is the story of the most audacious journey imaginable. Human species leaving its cradle, reaching into the black, and touching the face of the cosmos. It's a story of cold equations and white-hot courage, of political rivalry turned into peaceful partnership, and of machines we've sent ahead as our robotic scouts to places we are not yet brave enough or ready enough to go ourselves. It began not with a whisper, but with a scream, a single, terrifying beep. On October 4th, 1957, the Soviet Union launched Sputnik, a beach-ball-sized sphere of polished metal with 4 whisker-like antennas. It didn't do much, it just beeped. But that simple, repeating signal, heard on radios across the free world, sent a shockwave through humanity, and especially through America. It was a proof of concept that echoed around the globe. Literally, a human-made object was in orbit. The sky, the eternal domain of gods and birds, was now a place of machines, and we were behind. That beep triggered a panic, a frenzy of scientific effort, and a race that would define a generation. It was the starting pistol for the space race. The early years were a brutal learning curve, written in fire and heartbreak. The goal was simple, terrifying and unprecedented. Put a human being in space, and bring them home alive. The names of those first pioneers are etched in history. Yuri Gagarin, who on April 12, 1961, became the first human to orbit the Earth, reporting simply, "I see Earth, it is so beautiful." And then Alan Shepard, crammed into the tiny Freedom 7 capsule just a few weeks later, America's first answer. But these were suborbital hops, quick dips into the black. The real test was orbital flight, and here, the mission was not just about physics, but about nerve. John Glenn, aboard Friendship 7, circled the planet 3 times in 1962 while engineers on the ground held their breath over a faulty sensor warning his heat shield might be loose. He returned a national hero, having stared down the abyss and won. We were learning to live in space, minute by precious, dangerous minute. But then, the goalposts moved. In a speech at Rice University in 1962, President John F. Kennedy set a target so bold it seemed like fantasy. "We choose to go to the moon in this decade," he said, "not because it is easy, but because it is hard." The Apollo program was born. It became the greatest peacetime mobilization of technology and will the world had ever seen. It wasn't a straight line to glory. It was a path paved with sacrifice. The Apollo on fire in 1967 took the lives of Gus Grissom, Ed White, and Roger Chaffee during a ground test, a stark reminder that this work was deadly serious. From that tragedy came a relentless focus on safety. Then came the dress rehearsals. Apollo 8, at Christmas time 1968, didn't go to the moon to land. It went to orbit it, and from that distant vantage point, the crew read from the book of Genesis as humanity saw, for the very first time, an Earthrise over the barren lunar horizon hour, beautiful, fragile, blue and marble, alone in the immense darkness. It was an image that changed our consciousness forever. And then, July 20th, 1969, you know the words. Houston, Tranquility Base here. The Eagle has landed. For a day, the world held its breath. And then, a grainy, black and white image of a boot, a human boot, pressing into the fine, gray powder of the Sea of Tranquility. "That's one small step for a man," Neil Armstrong said, his voice crackling across 250,000 miles of vacuum. "One giant leap for mankind." Here's the part you don't always think about. Buzz Aldrin described the moon's surface as a magnificent desolation, beautiful and utterly empty. For 2.5 hours, 2 human beings hopped and bounded in 1/6 gravity, planted a flag, collected rocks, and became the only 2 living creatures not on Earth. They were the ultimate outliers, and they did it with less computing power than your modern smartphone. It was a triumph of human ingenuity, a moment of pure, unadulterated wonder. 5 more Apollo missions would land, each more ambitious, driving a lunar rover, conducting deeper science. And then, just as suddenly as it began, it stopped. We turned our eyes away. The door to the moon swung shut, seemingly for good. For decades, our presence in space became quieter, but in many ways, more profound. We learned to live there. The space shuttle, a revolutionary and flawed flying truck, gave us the ability to build in orbit. Its legacy is etched across the sky. The Hubble Space Telescope, launched in 1990 with a flawed mirror. It was given glasses by a daring shuttle crew in 1993. What followed was a revolution in our understanding of the universe. Hubble peered back to the dawn of galaxies, found proof of supermassive black holes, and showed us the ethereal beauty of stellar nurseries and nebulae, millions of light years away. It made the cosmos intimate. But Hubble's greatest successor in human spaceflight is the International Space Station. The ISS is the craziest, coolest, and most politically miraculous thing we have ever built. A partnership born from the ashes of the Cold War involving the US, Russia, Europe, Japan, and Canada. It's a structure the size of a football field, assembled piece by piece, in orbit 250 miles above Earth. It has been continuously inhabited by humans for over 20 years, a permanent foothold off our planet. Life on the ISS is a study in controlled weirdness. Water must be recycled from sweat and breath. Sunrises and sunsets happen every 45 minutes. Astronauts grow lettuce, fix toilets with homemade tools, and gaze at hurricanes swirling below them like living art. The science conducted thereon, human biology, fluid physics, materials sciences, preparing us for longer journeys. It is our prototype for a life beyond Earth, while we've been learning to live in low Earth orbit. We've also been sending our mechanical avatars to explore the solar system. These are the missions that carry our curiosity where our bodies cannot yet follow. The twin Viking landers on Mars in the 1970s were the first to search for life. The Voyager probes, launched in 1977, are now in interstellar space, carrying golden records with the sounds and images of Earth, a message in a bottle for any cosmic beachcomber. But the real rock stars of modern exploration are the Mars rovers, starting with the car-sized twins, Spirit and Opportunity, which landed in 2004. Opportunity was supposed to last 90 days. It kept going for 15 years, driving over 28 miles, a testament to brilliant engineering. Then came Curiosity, a nuclear-powered laboratory the size of a Mini Cooper, climbing a mountain inside Gale Crater, reading the Martian rock layers like a history book. And now, Perseverance. This rover is the most advanced robot ever sent to another world. It's collecting pristine samples of Martian rock and soil, drilling cores, sealing them in tubes, and leaving them on the surface for a future mission to bring back to Earth. And it has a sidekick in Ingenuity, a tiny helicopter that proved for the first time that powered, controlled flight is possible in the thin Martian air. These machines are our eyes, our hands, and our scientists on a world 140 million miles away. So, where do we go from here? After decades of orbiting Earth, the compass needle is swinging outward again. The Artemis program, named for Apollo's twin sister, has one clear, staggering goal: to return humans to the lunar surface, but this time, to stay, and not just to visit the familiar, flat seas. Artemis aims for the lunar South Pole, a place of permanent shadow and, we believe, vast stores of water ice hidden in craters that never see the sun. Water is the oil of space exploration. You can drink it, you can grow plants with it, and most importantly, you can split it into hydrogen and oxygen rocket fuel. Finding it on the moon means we could potentially build a gas station there, a waypoint for deeper journeys. The plan is to build a lunar gateway, a small space station in orbit around the moon, and establish a base camp on the surface. This isn't just about flags and footprints anymore. It's about learning to use the resources of another world. It's about proving we can live, not just visit. And the moon this time is not the final destination. It's the proving ground. The ultimate goal, the shining prize on the horizon, is Mars. Sending humans to the red planet is the hardest thing our species has ever contemplated. Their journey alone takes 6 to 9 months one way. The astronauts will be exposed to deep space radiation, to the psychological strain of immense isolation, to the total reliance on their machine for every breath of air and morsel of food. They will have to land on Mars in a spacecraft much larger than anything we've ever put down, survive for over a year until the planets align for a return window, and then take off from Mars, something we've never done with humans. The challenges are monumental, but the plans are being drawn up. We're developing new, powerful rockets, like SpaceX's Starship, designed to be fully reusable and carry 100 people at a time. We are testing life support systems that can close the loop, recycling almost everything. We are studying the effects of long-duration spaceflight on the human body through missions on the ISS. A human mission to Mars in the 2030s or 2040s is no longer science fiction. It is a difficult, dangerous, but achievable engineering project. Beyond Mars, the robotic vision expands even further. Missions are planned to Europa, an icy moon of Jupiter, under whose frozen crust a global salty ocean slosh is a prime candidate for extraterrestrial life, to Titan, Saturn's hazy moon, with its rivers and lakes of liquid methane, a bizarre, cold mirror of Earth's hydrologic cycle. We will send probes that can dive into the plumes of water vapor shooting from Enceladus, another icy moon, tasting them for the chemistry of life. We are building ever larger space telescopes, like the recently launched James Webb, which will peer through dust clouds to see the formation of the very first stars and galaxies, and analyze the atmospheres of planets around other stars, looking for the chemical signatures of botulogy for oxygen, for methane, for signs that we are not alone. The future of space exploration is a blend of human courage and robotic precision. It is both intensely practical and wildly visionary. We are on the cusp of becoming a multi-planet species, not in a dystopian escaping a ruined Earth sense, but in an expansive, pioneering sense. The knowledge gained, the technologies spun off, the perspective earned by seeing our world as a small, precious oasis, these are the real rewards. The story that began with a beeping metal ball is now about building a highway in the sky, with the moon as our first rest stop and Mars as the next frontier town. We are the generation that stands between the first footprints on the moon and the first footprints on Mars. We are the bridge. The journey outward is the ultimate expression of a species that cannot help but wonder what is over the next hill, across the next ocean, on the next world. It is our story. It is a story of reaching for the impossible, and in the reaching, discovering not just new worlds, but new depths within ourselves. We are stardust, yes, but we are stardust that dreams, that builds, that dares, and we are just beginning to learn what that stardust can do.